Okay, continuing with L'Hopital's rule. Remember, L'Hopital's rule is used when direct substitution yields the indeterminate 0 over 0, or plus or minus infinity over plus or minus infinity. We can apply it only to a quotient, but there are other indeterminate forms that are not quotients to start with. So they will require us to do some transformation before we can apply L'Hopital's rule. So let's look at an indeterminate product. Indeterminate products are of the form 0 times plus or minus infinity. All right, an example of such a form would be the limit as x approaches 0 from the right of x ln x. Now note I say from the right because, remember, the domain of the natural log of x is positive numbers only. We can't have x approaching 0 from the left. All right? If we plug in 0 here, we get 0 times, well, as x approaches 0 from the right, and as I have said so often in the past, it is always to your advantage to know what the graphs of common functions look like. You should know that the graph of y equals the natural log of x looks like this. As x approaches 0 from the right, the natural log of x approaches negative infinity. Right? Just knowing that shows you the domain, tells you that limit, all right? Knowing what that graph looks like. So what we have here is 0 times negative infinity, an indeterminate product. So in order to evaluate this limit, I'm going to convert that product into a quotient. We'll call it ln x divided by 1 over x. Okay, now, when we plug in a number approaching 0, we have negative infinity here. Again, you should know what the graph of y equals 1 over x looks like. And as x approaches 0 from the right, 1 over x approaches infinity. We have negative infinity over infinity, a standard indeterminate form. So now we can apply L'Hopital's rule. And remember, we want to be transparent. We want to communicate exactly what we're doing in each step. We're applying L'Hopital's rule. If you prefer an L, that's fine. Derivative of the natural log of x is 1 over x divided by negative 1 over x squared. Now I'm not going to plug in here. Before I do anything else, I'm going to simplify that algebraically. So what I have here is, and this is not L'Hopital's rule, this is just algebraic simplification. The limit as x approaches 0 from the right of 1 over x times negative x squared over 1. So we have negative x. As x approaches 0 from the right, negative x also approaches 0. And there's our limit by L'Hopital's rule. Okay, so that indeterminate product. We also have indeterminate differences, which again must be converted to a single quotient before we can apply L'Hopital's rule. All right, I'll just say infinity minus infinity. Indeterminate difference. Simple example, okay, that'll suffice. A limit, and just for clarity, we'll just say 0 from the right again, of 1 over the sine of x minus 1 over x. We have already seen that the limit of 1 over x as x approaches 0 from the right is infinity. 1 over the sine of x, well, as x approaches 0 from the right, the sine of x approaches 0 and is positive, so this is also infinity. So we have infinity minus infinity here. How do we turn that into a single quotient? By creating a common denominator. The common denominator is x times the sine of x. So if we multiply this by x over x, multiply this by sine x over sine x, what we have is the single quotient x over x. So we have x sine x over sine x minus the sine of x over x sine x. And now we get 0 minus 0 over 0 times 0, standard indeterminate form. So, by L'Hopital's rule, we have the limit as x approaches 0 from the right of 1 minus the cosine of x divided by, and we have to use a product rule here, 1 times the sine of x plus x cosine x. The cosine of 0 is 1. 1 minus 1 is 0 over 0 plus 0. We have an indeterminate form again. Well, that's the beauty of L'Hopital's rule. As long as we get an indeterminate form, we can continue to apply it. So once again, we apply L'Hopital's rule. We have the limit as x approaches 0 from the right of sine x, that is the derivative. The derivative of cosine x is negative sine x, negative sine x, over cosine x plus, again we have a product rule, 1 cosine x plus x times negative sine x. Equals, the sine of 0 is 0, 1 plus 1 minus 0, 0 over 2, which equals 0. And there is our limit. Okay, those are relatively straightforward. We simply convert to a single quotient and we apply L'Hopital's rule. We have another group of indeterminate forms, however, which are a little bit trickier. And for these, we have to take what I like to call a backdoor approach. But it's an approach that you have seen before in a different context. These are indeterminate powers. And the indeterminate powers are of 3 forms. If direct substitution yields any of those, then we're going to have to do some work. And this is going to be different in that we are not going to be able to evaluate those limits directly. What we're going to have to do is use a natural logarithm. And we're going to be able to evaluate the limit of the natural log of the original expression. And then rely upon one simple fact. And that is this. If the log of something, whatever it is, I'll just call it x, is something, y. If that's the case, if the log of x is y, then x equals e to the y. Right? If the log of x equals y, then x is e to the y, rewriting the logarithmic expression as an exponential. logarithmic equation as an exponential equation. So we're going to be able to find the log of our original expression, and then the limit will actually be e raised to that, the limit of the original expression. So let's go. Let's do one example here of one of these. Find the limit as x approaches infinity of x to the 1 over x. I said we had seen this approach elsewhere, and where we saw this approach, taking the log of this, was when we did logarithmic differentiation. You'll remember at the time, we said we cannot directly differentiate a variable expression raised to an exponent that is also a variable expression. We have to take the log of it and then do the derivative that way. Well, the same thing applies to this limit. Right? We can't find that limit directly, but we can find the limit of the log of this. Right? So, if we plug in infinity here, we get infinity to the 1 over infinity, which is 0. We get infinity to the 0. So, I am not going to write an equal sign here because the limit I am about to evaluate is not that same limit. It's the limit of the log of that. I am going to take the limit as x approaches infinity of the log of this expression. Now, you'll remember, I hope, from our properties of logarithms, that the log of x to the a equals a ln x, the log of. So, the log of this expression is 1 over x ln x, which we will write as ln x over x. And we plug in infinite value here, and we get infinity over infinity. A standard indeterminate form. So now we can apply L'Hopital's rule to that limit. And we get, by L'Hopital's rule, a limit as x approaches infinity of 1 over x divided by 1, which is 0 over 1, which is 0. Which means that the limit of this is e to the 0, which is 1. And that's the way these indeterminate powers